In part 3 of lecture 1, we will look at an example of the compiling process. Let's take a look at an example of the process of compiling a program. This is the program that we're going to start off with. It is obviously written in C. It begins with the usual int main, and then you have three variable declarations: float average, int x3, meaning that x is an array of three integers, int I sum. Now you'll see here we're going to explicitly set the three values in x. x0 is 3, x1 is 6, and x2 is 10. We will initialize the sum to 0, and in a for loop we will have I go from 0 up to 2. When it hits 3, we'll drop out. We're going to add x sub I to the sum. Now that we have the three added together, we will find the average, which is sum divided by 3, and returning 0 means the program will return control to the operating system with a status code of 0, meaning it terminated normally. What you should notice in this, although it's easy to miss if you really think about it, is that there are no input or output statements. The reason that I did this is to leave out one particular factor for the moment, namely that we need some kind of runtime library to allow us to handle input-output. Obviously, in a real compiler, you have to do that, but for the sake of this simple example, we're leaving it out. Let's take a look at the token that the lexical analyzer will provide for us. We start out with int, identifier, open parenthesis, close parenthesis, open brace, float, identifier, semicolon, and so on. Int here is a token that matches to the character string int, and you'll notice that you'll see here several occurrences of ID, or short for identifier. This is going to be used as a token for main, average, x, I sum, and so on. You'll notice several instances of literal. This refers to 3, 6, 10, 0. These are literal values that we see in the program. Some tokens have a one-to-one correspondence with certain strings. And again, identifier is a token that we will use for the various identifiers in the program, as I said earlier. You can see in this slide a sample parse tree. Although, as I said earlier, we are not typically going to actually produce a parse tree. You can see at the top the non-terminal program. You can see below it the non-terminal function definition. You can see after that type specifier, and finally the token int. Now you'll notice that there's a lot of things that seem to be in here where we can make a good case that we don't necessarily see the need for to save a great deal of this. Now, this is one of the things that makes saving a parse tree not just complicated, but taking up a lot of memory that we may not need. However, going through this process is important because this allows us to recognize what is what within the program. What we will find later is that syntax plays a sizable role in our understanding the meaning of what our programs are all about. Here we can see an example of an abstract syntax tree that we can build based on the program that we've had so far. The ID at the top refers to main, our main program in this case. We can see from working children left to right that its return type is integer, that it has no parameters, and that there are declarations for variables within the main function. And you can see here that there are three identifiers. We can see next to it the collection of statements that we have. Now, presumably, that we are going to have annotations for the three identifiers below, indicating what their types are. and other relevant information about that, and next to it the statements. This is not the uniquely correct way to do it. By that I mean this is one way that we can, and there are others that we might also look at that would also be correct, but this is the one that we're looking at just in this one example. Here you can see the intermediate code for the program illustrated earlier. We are using quadruples, or 3 address codes, as our intermediate representation. The name quadruples indicates that there is one operation and up to 3 operands, indicated by their addresses in each statement. Main, T1, and T2 have label as their operation. Main, T1, and T2 are addresses within the code to which we can begin execution or jump within the program. We have assignments for all 3 elements in the array X, with X0 set to 3, X1 to 6, and X2 to 10. Here the operation is assignment, and the operands are the array X, the index of the element, and its assigned value. We also assign values to sum and I, but here there are only 2 operands, the variable and the value assigned to it. If I is greater than or equal to 3, go to T3 has as its operation if greater than or equal to go to, and its operands are I, 3, and T2. Sum is equal to sum plus T3 has as its operation add, and its 3 operands are sum, the new value, sum, the previous value, and T3. Go to T1 has as its operation go to, an unconditional jump, and 1 operand, the label to which it is jumping. You can see on the side markings that indicate the ranges of instructions within 2 basic blocks. These are blocks of code that will always be executed as a unit. This becomes important because they can be optimized easily. Global optimization requires that we trace our way from one basic block to another, which is more complex than the local or peephole optimization within a basic block. This slide shows assembly language code for the program we illustrated earlier. It's not the entire program because it runs much longer than one slide. The first statement basically is there to indicate to the compiler that this is going to be a near procedure within the same segment as whatever else you have. The first 3 statements, basically are about saving the value of the base pointer, moving the value of the current stack pointer, in other words, the top of the stack, into the base pointer, and then subtracting 88 from the base pointer. In other words, what you are doing is saving as a bookmark the previous top of the stack, and then in effect adding 88 bytes of storage to it, so you have room for the local variables. The EBX, ESI, and EDI register contents are pushed onto the stack so they can be restored later. Below you see how values are saved here. The 3, 6, and 10 for the array X are saved here, as well as the value for sum. These are all on the stack because this uses stack dynamic memory for these and frees up the space afterwards. For a compiler to translate a program from a high-level language to any other language, low or high level, it needs to be able to keep track of all the data regarding the various symbols that show up in a program, whether they are reserved words, whether they're identifiers, numbers, other literals, operators, or so on. And for that reason, what we need is something like the symbol table. It includes information about all of the symbols that you'll see in a language, the keywords or reserved words, the standard identifiers, the identifiers that are defined by users, whether they are constants, variables, or data types, the various literals that you can have, including numbers and characters. And we have to store this in one place with all the necessary information about them. For every symbol that appears in a program, we need to store certain information. We need to store the token or token class, some representation of the element within the programming language that this symbol represents. The lexeme or string, what the actual string is that we find in our program. The scope, where within the program does this symbol appear? Is it in the entire program? Is it through a particular method, or is it in some block of code within the method? The data type, and pointers to other symbol table entries, such as a data type defined by the user that this variable belongs to, or the length of an array. These things have to be stored there as well.